already read about
Yes,
the
sir.
heat
So
transfer?
হ্যাঁ স্যার পড়েছি স্যার।
yes, sir. পড়েছি স্যার, ফিন হিট ট্রান্সফার পড়েছি।
হিট ট্রান্সফার পেপারটা পড়েছো, সেখানে ওয়ান ডাইমেনশনাল স্টেডি স্টেট হিট কন্ডাকশন ইকুয়েশন থ্রু এ ফিন নিশ্চয়ই পড়েছো।
Yes, sir. ফিন পড়েছি স্যার, সার্কুলার ক্রস সেকশন।
Now we start with the idea that actually this experiment is about the object of the experiment. Name of the experiment is heat transfer from a pin fin. And the object of the experiment is to find out, কার্সারটা কি দেখা যাচ্ছে?
স্যার দেখা যাচ্ছে।
হ্যাঁ স্যার, দেখা যাচ্ছে।
আচ্ছা, object of the experiment is to find out the heat transfer coefficient and rate of heat transfer through the pin fin. And then number 2 is to study the temperature distribution along the length of the fin, of the pin fin, or forced convection. Now, important aspect about this is that why we are doing the experiment, that reason is that, as you know, that this fin is basically a projected surface from a certain surface. That means suppose we have to carry out a heat transfer between a solid surface and a fluid. Just think of that situation, that we have to have a heat transfer between a solid surface which is heated. Normally the solid surface is the heated surface, and the heat has to travel to a fluid which is surrounding the solid surface. Now this fluid surrounding the solid surface may be either a static fluid. In that case, there will be conduction to certain extent and natural convection. And if that fluid is not static, if it is a moving fluid, and it is moving because of some forcing device like a fan or a blower, then the heat transfer will be predominantly by convection. Conduction will be very, very insignificant, and it will be mostly convection and forced convection. So hopefully you have read about this convection, conduction, and forced convection, and natural convection, and radiation, everything you have read. Now we will have to explain the this heat transfer related theory in connection with this experiment to the extent possible, but sometimes it may need some more in-depth study. So for that, I'll suggest you to refer to the book by Incropera, which you have already read, I think. And there is another very good book that is Nekati Ojisik. That is also a good book. You know that book is also available in the market, in the library. That is a good one. Another book is also very good, that is regarding heat transfer by, I think, Thompson. Another book is there by Sengel. So you can take any of the textbooks. Now to start, let me tell you that fins are projected surfaces. Projected surfaces. What is a projected surface? Suppose we have got a surface. We have just a surface, flat surface. And surrounding the flat surface, there is a fluid. We have to transmit heat. Now, thing is that, as you know, that whenever heat travels by convection from a surface to another fluid adjacent to the surface, then the rate of heat transfer is guided by a law which is called the Newton's law of cooling. And this rate of heat transfer is proportional to the area of the surface which is exposed to the fluid, that is, which is perpendicular to the direction of heat transfer. That is one thing, that is proportional to A. Q convection is proportional to A, the area of heat transfer, and it is also proportional to the temperature difference existing between the surface and the fluid, that we call delta T. Combining these two, we can say that Q convection, rather you can say Q dot convection, that is the heat transfer per unit time due to convection, is equal to some constant H into area A into delta T. This you know. Here we have defined a constant H in order to get rid of the variation sign, and this H is called convective heat transfer coefficient. Now about this convective heat transfer coefficient, you have learned a lot. You have seen that there are different types. There are different parameters on which this convective heat transfer coefficient depends. It is supposed to be a constant when we think about removing the sign of variation and connecting it by a equation. But H is strictly speaking dependent on many parameters. One of the parameters on which the convective heat transfer coefficient depends is the velocity of the fluid. And you have read out it. It also depends on the surface details. That is whether the surface is rough or whether the surface is having a high polish, all those things, and what is the material of the surface. That is also important, and lots of other things are also there. We are not going into the detail at the moment. What we are now trying to tell you is that if we want to increase the rate of heat transfer from the surface to the fluid, then what we do? We can either increase H, or we can either increase area of heat transfer, or we can increase the delta T. Now, when we investigate these things, delta T, that is the difference in temperature, which is the forcing function, cannot be increased to any level in order to increase the heat transfer rate. And because the heat transfer is generated because of this delta T, and we are studying the convective heat transfer with a certain value of delta T in our mind. In case of a heat transfer from a solid surface to a liquid or a gas, delta T can have some value, but it cannot be always changed like that. We cannot increase it to a very high value in order to augment the heat transfer rate. Now, the important thing is to augment the heat transfer rate. We want to increase the heat transfer rate. Second thing is to increase the H, convective heat transfer coefficient. That again is also a very difficult thing. We can change the value of H, that is correct, but we cannot increase it to anything as we want. We cannot increase it to any level. There may be changes. It depends on the velocity of fluid. It depends on Reynolds number. All these things. That is true, but still there is a limitation. We cannot increase it to any level. So, in order to augment the heat transfer, the easiest way, the cheapest way, is to increase the area of heat transfer. And the fins are actually projected surfaces. So when we have a flat surface between a fluid and its hot body, when we have a flat surface, that is the interface, we want to form projections on that surface. That is, increase the height of the surface and give it a certain shape, either a rectangular projection or a triangular projection. We want to give it a projection. That projected surface, in order to augment the heat transfer, is called the fin. That is one thing that you know already. Then we come to, after knowing the fins, what are the applications of fin? That is, one application is in the engines, which we will discuss, the internal combustion engines. And there, the motorbikes also you have seen. engines become hot during combustion of the gases. So heat has to be quickly removed from the hot engine. If we cannot remove it quickly to atmospheric air or to any other fluid, then the engine will become overheated. If it is overheated, there will be lots of other problems, thermal stresses, etc., etc. So for engines, it is important. For electrical motors, electrical generators, for the steam turbines, for the gas turbines, for the aeroplane engines, for the aeroplane turbines. You see, for all such devices where huge amount of thermal flux is involved, we require cooling, and cooling for that we require a fluid also for carrying away the heat. But between the fluid and the hot surface, we have to have fins. In air conditioning, now I am coming back because air conditioning is the field where I have worked. I have seen lots of fins there. It is a must for having effective heat transfer, augmented heat transfer rate between the chilled system and the air. So fins are very important. Now we are interested to study the heat transfer coefficient. We want to find out. This is one thing. Second thing is the rate of heat transfer through the fin. And also you want to study the temperature distribution along the length of the pin fin for forced convection. Now coming to the apparatus. Apparatus, they have explained the apparatus here. Okay. Now I want to, you can read it later at your convenience. I want to explain it through a diagram. In our case, the fin is like this. This is the fin. This is a rod basically. A rod having diameter maybe 10, it is 1.27 centimeter, 1.27 centimeter. That means a half inch diameter. Half inch is not a very big diameter. And rod length is around, this A is 3 centimeters. So 12 centimeters plus 0.5, 12.5 centimeters is up to this. That is 5 inches. So half inch diameter and 5 inch long, and this portion is also maybe 1 inch or something like that. So this is the thing, a rod, and one side of the rod is inside a coil. So this is the coil, inside that the rod is introduced, and this coil is the heating element. How we are heating? We have got a heater terminal here. From a heater, we are connecting these two, where electrical heating is done. So this end of the fin will be very much heated. What we are doing is that we have got a duct. This is a duct basically. Duct means this is side view of the duct. If you look at the top view, that is also this sort of thing. That means this is a rectangular. If you take a cross section, it is a rectangular cross section. This side is like this, that side is something like this. It's a rectangular cross section, pipeline. This is not cylindrical, this is rectangular. And one wall, on that wall is mounted this heater, this entire assembly. This entire assembly is mounted. So there is a hole on the wall. We have made a hole on the wall. There is a hole on the wall, and through that hole we have inserted this rod, which we call a fin. And the heating coil is touching the ducts, right? And the heating coil is getting its input From a, there is an electrical panel and all these things are there. We'll complete later. But for us, it is important that the rod is heated and the rod is not going up to the end of this duct. You see, this duct has a width. We'll see how much is the width. Now, the rod is not going up to the end of the duct. Most probably it is going around, it is going to the half the width of the duct it is going. So another half is there. So, and it is surrounded by air which is there inside the duct. So I think you can now visualize inside air there is a rod, and this rod is starting from a surface. That surface you can say is this surface, and this rod we are calling a fin. And it is, what kind of a fin it is? It has got a constant cross section area and length is quite big compared to its cross sectional diameter. We call it pin fin. No, it's not like a pin, but we call it pin fin. And this side we have got a blower. It's a side view of the blower. If you look from this side, this is not the side view, I'm sorry, this is front view, of course. Side view will be a circular one. This looks a circular thing. Side view is, I mean, we are standing in this side, so front view is like this, and the side view will be circular. So it is a centrifugal blower. There is an electric motor. Powered, when it is getting its power, it runs the impeller here, and that draws in air from the outside of the atmosphere through this, you can say, pipeline, which is rectangular cross section, into, this is a flange you can say. This duct has a flange, and this blower also has a flange. They are connected here. So the air is flowing through this into the eye of the blower, then it is coming centrifugally, it is going. Centrifugally it is going, it is a centrifugal blower, and it goes through this pipeline. This is a pipeline, and we have a valve here for starting and stopping the airflow. And we have got a two flanges here, and here we have got a plate. Centrally, it is having a hole. That plate we call a orifice plate, which is having an orifice hole. That orifice is meant for providing some resistance in the path of air. It was, first of all, it was initially not necessary for us to put a resistance in the flow of air, but we are doing it willfully because we want to measure how much air is flowing through the pipeline. In order to measure that, we require this orifice plate. There are many ways to record the airflow quantity. One way is to insert a orifice plate. And when the air flows through the orifice plate, it suffers a huge pressure drop. And there is a pressure drop between the upstream side. This is the upstream side. The air is flowing on this direction. And I'm sorry, the pressure incoming side of the orifice, the pressure is high. Outgoing side, it is low. So if we connect an U-tube manometer to the two terminals is already made here. This U-tube manometer is provided with water as the fluid. So the water will surface on the two sides, will be experiencing differential pressure. Pressure here is high, static pressure, here it is low. So this surface will be lowered and this surface will be upward. And the difference between these two surfaces is measured by a scale. Measuring that difference, there is a formula by using which we can find out how much is the air flow through this orifice. Now, when we know the airflow quantity, why we are measuring that? When we know the airflow quantity, yes, any question? YouTube manometer. Acha. Yeah, should I explain again? In this, it is basically YouTube. It's called a manometer because it measures the difference in pressure between its two tapping points. In terms of the pressure difference is recorded in terms of the height of a water column here. It may be mercury column also, it may be any other fluid column also. Here the fluid is water. And depending on the height, this is basically the pressure difference between these 2 points. In the pressure head, if you convert this pressure in static pressure head, this pressure in static pressure head, the difference in the heads, P by gamma here and here, that is recorded in the height. Now, this height, from that there is a relation. That relation I will tell you. We can find out how much air is flowing, volume flow rate, Q. This is not heat flow rate, how much volume flow rate of air is going on there. And as you know, the volume flow rate is a product of the cross-section area of the flow passage and the velocity. Now, here the cross-sectional area is smaller compared to the duct, so the velocity is quite high, but inside this duct, the area of cross-section is quite high, so the velocity is lower compared to that in the pipeline. Now that is the velocity with which the air is striking the surface of the fin. If we come back to the fin, this is the fin. We have got 5 equidistant points, 1, 2, 3, 4, 5, on which we have mounted 5 thermocouples, hot junctions. Hot junctions of 5 thermocouples are mounted here, because thermocouple, as you know, that two wires are connected at the ends, and one is called the hot junction, which is recording the high temperature, and the other is the cold junction, which is the ambient, which is there in the atmosphere. And 5 thermocouples are there, and at the end we have got a wooden piece which does not allow any heat to flow in the axial direction. Now here the heat transfer which is occurring, we are assuming the heat transfer to be one dimensional or one directional, you can say. That direction or dimension is the length of the rod. As you know, if you express it in the cylinder, this cylindrical rod in the cylindrical coordinate system, this axial coordinate is Z. That is the one dimension, the axial dimension. And radial dimension is R. And then there is a circumferential angular dimension, that is theta. So in this particular case, we are assuming that when we are heating up one end of the bar, we are starting from this end. We are considering this is our fin base. And the temperature here is T1. Here it is T2, T3, T4, T5. T1, T2, T3, T4, T5 are known to us by experiment. And heat is flowing in the direction of the axis of the rod. So that is our assumption. And we are also considering that in the R direction, there is no gradient of temperature, so that there is no heat transfer. And in the theta direction also, there is no gradient of temperature. Entire gradient of heat temperature is remaining in the axial direction, Z direction or X direction. If you want to write X, you can write X also. X direction. Let's say X direction. The temperature gradient exists. So from one cross section here to the next cross section, the heat transfer occurs, and that from that to the next cross section. And we are assuming that each, if you consider any cross section, circular cross section, all the points of that circular cross section, the temperature is uniform. So if you consider, if you cut it, there is a circular cross section, temperatures at all points in that circular cross sectional face is considered to be equal, same, because we are not we are neglecting heat transfer in the R direction. So R direction there is no heat transfer. So all the points must be at the same temperature. With R there is no variation of temperature. So the last point, there is a peripheral point, circumferential point of the cross section is also at a temperature same as the temperature at the center. That is, the entire cross section is at the same temperature. But when it goes to the next cross section, there is a drop in temperature, and the drop is only occurring in the x direction. So there is a dt dx in the x direction. That is one thing. Second thing is that we are also assuming that we are taking the readings T1, T2, T3, T4, T5 not at the beginning of the experiment where the temperatures are changing. When you start just heating the one end of the rod, temperature increases in this at this point as well as at this point. In every point, the temperature gradually increases. This is called the transient zone, where the temperature increases at each point, at each cross section. At all points in the cross section, the temperature is increasing with time. That is called the transient state. And after the transient state is over, we go to the steady state. And in that steady state, the temperature remains same at all points. I mean, not at all points. Temperature remains same at a particular cross section with time. With time, there is no change in temperature at a particular cross section. That is called the steady state. So the experiment is about heating up of this film and maintaining steady state and then recording the temperature at these points. 5 points, as well as at the temperature of the film air which is surrounding this, that also we are recording. So after we do that,
Sir, what is the purpose of the
Yes.
thermocouple?
hello,
Sir? Sir, what is the purpose of the thermocouple, sir?
thermocouple, the function, you want to know the function is to measure the temperature, record the temperature.
Oh,
It
okay, sir.
is a device. Thermocouple is a measuring instrument for temperature. So its theory is that they say there are two junctions between two wares, conducting wares. It may be chromel, alumel. One half may be chromel, half may be alumel, or copper constant, and it may be the character is that the two junctions, if you keep them at different temperatures, then a EMF gets generated between these two junctions and a current flows through the closed circuit of the two wires. That is the theory. That is the Peltier effect. I think you know that. And
Yes, sir.
and you see, when you keep the two junctions at different temperatures, then an EMF is created, which is a very low EMF, and a very low current flows through the circuit. Now, if you can record the EMF difference between the two junctions, that is the hot junction, one is called a hot junction and this is called the cold junction. If you can record how much is the voltage difference, EMF, potential difference between the two junctions, then by recording that, you can measure the temperature difference between these two junctions with the proper calibration of the thermocouple. So the thermocouple calibration, if it is done, then by recording the temperature EMF difference between the hot junction and cold junction, we can find out the temperature difference between the hot junction and the cold junction. And if any junction temperature is known to us, suppose the cold junction temperature is known, here it is the atmospheric temperature, then we can find out the temperature of the hot junction. That is the temperature which we want to record. Now about the setup, another few things I'd like to tell you. Here we have DP-dt switch dipole di-terminal switch, I think, electrical item. And here we have a temperature indicator, which is a digital device. It was initially not digital, but now I think it has been made digital in our setup. So there are some selector switches. By rotating them, we can get the different temperatures at T1, T2, T3, T4, T5. All these temperatures we can get here. And the thermocouple ends are connected. There is a terminal box for the thermocouples. The thermocouple ends are connected here, and this is the control console. And this is called the dimmer-stat. Dimmer-stat or variable transformer. This is basically a disk. This disk can be rotated, and it is a transformer sort of thing. It has a primary and a secondary winding. Primary winding gets the CSC voltage of 220 volts. Secondary winding has got a large number of turns, which can be changed by rotating this disk. So if you rotate the disk, you can change the number of turns of the secondary winding, and the PD, potential difference, across the secondary winding can be changed. Now, we have a stipulation that the heater here cannot withstand a voltage as high as the CSC supply voltage. So by rotating this, we will allow just the desired voltage to come onto the heater, which may be 80 volts or 100 volts or something like that. That is called a dimmer-stat. So that is the experimental setup which we have explained. That's why I'm not going through this now. It's a brass fin, of course, of circular cross section, and the apparatus is manufactured by Polylab. And this sizes, duct size, diameter of the fin, all these things. And diameter of the fin is 12.7 millimeter, and diameter of orifice, etc., etc. These things I'll be giving you later. I'll fill up all those things and I'll hand over to you. Now, theory is that whenever we consider one-dimensional steady-state heat conduction through the fin, the equation governing a differential equation is this: d2 theta dx2 minus m square theta is equal to 0. Now this equation is basically, theta is a difference in temperature at any point on the fin, minus the fluid temperature, Tf. Tf is the dark fluid temperature, and T is the temperature at any point, at any value of x on the fin. Right? X is 0, and where temperature is T1, x is 0. So as x increases, T also decreases, and T minus Tf is gradually decreasing. That is called theta. And d2 theta dx2 minus m squared theta, that is equal to 0, where m is a constant. M square rather is Hp by Ka. H is the convective heat transfer coefficient on the surface of the fin, P is the perimeter of the fin, and A is the cross-sectional area of the fin, and K is the thermal conductivity of the fin material. All these things are written here, right? But one thing, this K is capital, this K is not in capital. You can think that this is small k, right? There are some printing mistakes here and there. And the equation, general solution of this differential equation is theta is equal to C1 e to the power mx plus C2 e to the power minus mx. Here we have to apply some boundary conditions so that we can find out C1 and C2, which are the constants of integration, because this is integrated twice in order to get the solution. And in order to get that, we use the boundary condition. There are two boundary conditions. One boundary condition is that theta 1, that is where temperature is T1, then theta 1 is T1 minus Tf. That is known to us. I mean, that is theta is known to us where x equal to 0. We can say where x equal to 0. Where is x equal to 0? We consider here, we consider x equal to 0, and the value of theta here is considered theta 1, and which is T1 minus Tf, and which is known to us. And that is one boundary condition, that x equal to 0. You put x equal to 0, you'll get some relation C1 plus C2 is equal to theta 1. Then second thing is d theta dx is equal to 0 at x equal to L. L is the length of the fin. This length of the fin we consider in this direction is the L. And at x equal to L, we consider, say, this is up to, this is the L. And at x equal to L, we have a wooden block, so that there is no heat transfer here. There is no heat transfer. Wooden block means there is no heat transfer in the x direction. So if there is no heat transfer, because you know heat transfer is minus k into a into dt dx, or k into a into d theta dx. So if heat transfer is 0, then d theta dx at this point is 0. That is at x equal to L. So that is our second boundary condition. At x equal to L, d theta dx equal to 0, and putting these two boundary conditions here, I mean, we can get this exact solution. That exact solution is T minus Tf, T minus Tf, that is theta, which is a value, by T1 minus Tf, which is theta 1, the base fin base temperature being T1, that is cos hyperbolic, that is equal to cos hyperbolic m L minus x by cos hyperbolic ml. Now x is the distance from the fin base, L is the length. M is known to us. Now based on this, if we put the value of x, at any value of x, we will get a value of t, and for that we get a value of theta. So in our experiment, what we do, first we measure T1, T2, T3, T4, T5. So that is the experimental value at x1, x2, x3, x4, x5. Secondly, from this solution also, putting different values of x, we get T1, T2, T3, T4, T5. And we'll have to check whether this solution will corroborates with the experimental solution. Then heat flow rate through the fin at x equal to 0, that also we can find out that at x equal to 0, from this relation, if we differentiate, we'll get theta d theta dx. D theta dx we can find out, and this d theta dx is at x equal to 0, the value of d theta dx is the heat flow rate. So whatever is the value of d theta dx, that we find out, and that becomes, this is basically q, this is not theta, this is the heat flow rate through the fin at x equal to 0, that is equal to root over hpk into T1 minus Tf into tan hyperbolic ml. So that is your, and these relations are there in the book by Ojicic, Introperalge. The effectiveness of the fin can be calculated as this. Now this is basically wrong. This is not the effectiveness, you correct it, this is efficiency. This expression is efficiency. This is q by, this is not theta, right? This is q actual by q maximum. Q actual by q maximum. Q actual by q maximum, that is equal to tan hyperbolic ml by ml. This is also given in the book. You can find out this. This is the fin efficiency. And fin effectiveness, which is the ratio between the heat transfer rate with fin by heat transfer rate without the fin. This is heat transfer rate with fin divided by maximum heat transfer rate from the fin, where this is Q max, that is the rate of heat transfer from a similar fin of infinite thermal conductivity. If we consider that the fin thermal conductivity is infinite, then the fin base temperature and the fin surface temperature is same. Just you look at the fin again. In this fin, if the fin base temperature and the fin surface temperature up to the end are all equal, that means that there is no temperature drop in the through the fin. That means the thermal conductivity is infinity through the fin. That means the thermal resistance is zero. So under that condition, whatever is the heat transfer rate from the fin surface, that is the maximum heat transfer rate, and that is used in the denominator. So that is here the efficiency, and this is Q by Q max. Again, Q fin by Q non-finned or Q unfinned, that is the effectiveness that you can see from the book, the expression you can find out. And these are the things that you have to find out. Now for that, for everything to be done, you have to find out M. If you do not know what is M, you cannot do anything. In order to find out M, you require M is equal to root over HP by K. Now P is known, A is known because fin geometry is known, and K is the thermal conductivity of the fin material. That is also known. Only unknown is H. The H, that is the heat transfer coefficient, convective heat transfer coefficient, that you have to find out. Now, how to find out that? For that, here you have a quantity which is called the Nusselt number, which is HD by K. This H is the convective heat. This is for convective heat transfer through a cylindrical rod. D is the diameter of the rod and K is the thermal conductivity of the fluid surrounding the rod. This K is not this K. Mind that this is small k. That is, this K is equal to this K, the thermal conductivity of the material of the rod, and this K is the thermal conductivity of the fluid. So if you know the D and K, and if you know the Nusselt number, then you can find out H. That is how you have to find out H. So how to get it? So you have to get the Nusselt number. Now you see, for a forced convection, Nusselt number is related to another number. Nusselt number is a non-dimensional number. It is basically the ratio between the convective heat transfer rate and conductive heat transfer rate. Now it is there is a relation of Nusselt number with Reynolds number and Prandtl number. Actually, Nusselt number is equal to some constant A into Reynolds number to the power B into Prandtl number to the power C. That is the relation. Now that relation has been derived for different values of Reynolds number. Reynolds number can be from 40 to 4000, or it can be from 4000 to 40,000. They have considered two ranges. This Reynolds number is, as you know, that is a ratio between inertia force and viscous force. This rho Vd by mu, this d is the diameter of the fin, and v is the velocity of the fluid, and rho is the mass density of the fluid surrounding the fin, and mu is the dynamic viscosity or coefficient of dynamic viscosity of the flowing fluid. So this mu you can get from property chart, rho also you can get from the property chart, d also is known, but v has to be determined. So now the entire problem goes to the determination of the velocity of the fluid. So in order to determine the velocity of fluid, what we do, now these are the readings that we have made. This third reading where H is 0, where the manometer reading in centimeter of water column is 0, this is to be neglected. This reading you don't consider. And these two readings, I consider temperature readings are given T1 to T5, and this is the fluid ambient temperature 32 degrees Celsius. This is not there. So this has been, this you can utilize this. And the calculations are like this. You first of all consider the average fin temperature, not film, average fin temperature. That is fin temperatures T1, T2, T3, T4, T5, and take an average of that. And that average temperature minus the fluid temperature, that is the delta T. And there is a mean film temperature. This is mean film temperature, that is the mean of fluid temperature and the average fin temperature. So you find out the average fin temperature and plus fluid temperature divided by 2, that is the mean film temperature. And this mean film temperature minus the fluid temperature, that is delta T. Now come to the volume flow rate through the duct. So volume flow rate is, this equation is derived from the theory of fluid mechanics, and you can check the book by Seeley. I'm sorry. You can check the book by, yes, you can check the book by Massey, B.S. Massey, or Shigley. But you check the book by B.S. Massey, or you can check any other book on fluid mechanics. This relation is derived there. This Q dot is the volume flow rate per unit time, how much volume is going, volume of air is flowing. CD is the coefficient of discharge of the orifice. This CD value is 0.62, and pi by 4 into diameter of orifice whole square. This diameter of orifice is also given, known to us. I'll give you. Root over 2G, G is known to us, 9.81. HW is the water head, a manometer head in centimeter. I'm sorry, meter of water. It is in meter of water. And rho W and rho A are the densities of water and air, respectively, available from property tables. So with this, we can find out the velocity of air at the temperature TF, that is fluid temperature, that is Q dot by A. This Q dot that we get from here is divided by the area of the duct. You get the velocity of air at TF, and A is the duct cross-sectional area. Now we are interested in the velocity of air at T mean film temperature. So for that, we have to use this relation. The ratio between the temperatures is equal to the ratio between the velocities. So from that theory, we can find out the velocity of air at T MF, mean film temperature. So you get that. Now from that velocity, you can find out the Reynolds number. And knowing the Reynolds number, you can see the Reynolds number may be either, what is the value of the Reynolds number? If it is in this range, then you use this relation and get the value of Nusselt number. If the Reynolds number is higher than 4000, use this and get the Nusselt number. From the Nusselt number, you can get the value of H. So that is your basic objective. That initially the objective was to find out the heat transfer coefficient and the rate of heat transfer through the pin fin, that also is given. To study the temperature distribution and the length of the pin fin for forced convection. Now this study we have made experimentally, we have done, and from the theory also we have done this study. Experimentally we have recorded T1, T2, T3, T4, T5. We can plot T with respect to X, and we can, with different values of X, we can get the value of T1, T2, X, theoretically also. Now your job will be to, this is the procedure, and plot the temperature distribution along the length of the fin from the observed readings. So length of the fin along x direction, t along y direction, you find out the plot. Calculate the value of m. M value you have to find out. Root over hp by ka, and obtain the temperature at various locations along the length of the fin. Knowing the value of m, you can, from the relation, that solution which we have got, from that, for different values of x, you can find out the temperatures at different values of x, plot them to get the theoretical distribution. So now you can superimpose one plot on the other. On the same sheet, you can make the plot based on the observed readings as well as based on the calculated values, and you can see how the values are telling or not. I mean, how they are different. That is one thing. And secondly, the Reynolds number, Nusselt number, these can be, Reynolds number and Nusselt number can be calculated from the relation that you have to show, and calculate the heat transfer coefficient. That also will do it. Knowing the Nusselt number, rate of heat transfer is also known, Q dot. Fin effectiveness, fin efficiency and effectiveness, both you have to do. You repeat the same procedure for all other sets of observations. Now we have taken two sets of observations, observation set 1 and 2. For both of them, you have to find out this. So your discussion will be comment on the observed temperature distribution and calculation by using the theory. Comment on the change in H with free and forced convection for the same fin. Here we have got forced convection. Free convection is not there. You just write the comment that the value of H will be much lower for free convection. So how it increases the heat transfer rate for forced convection? For that, you have to justify that H increases because of forced convection, and also in case of turbulent flow, this H becomes maximum. So the heat transfer rate is also maximum. So that you write, and that is the experiment. You have to put your name here and other things. Some data which are not given in this sheet. This sheet I am giving you, sending to you, and certain data which are required also I'll be tomorrow I'll be sending to you. Okay. So that is our experiment. Hello.
Yes, sir.
Yes, sir.
So I'll request if there are certain things which you could not understand, then you can tell me. Okay.
স্যার ওই মানে ফিনটার পজিশনটা একটু বুঝতে পারছি না, মানে কিরকম পজিশনে থাকে ওটা?
কোনটার?
ফিনটা।
হ্যাঁ
স্যার,
ফিনটা তো আমি বললাম, ফিনটা হচ্ছে, you see this, as I told you, that this is a duct, DUCT duct. Duct is basically a pipeline, channel through which fluid flows, air flows. Now this duct can be circular cross section or can be rectangular cross section or can be square cross section. In our case it is rectangular cross section. So this is one side, there is another side perpendicular to that, and on this surface we have made a hole, and through that hole we have inserted the fin. This fin looks like a rod. So this end goes to the center of the up to the center of the duct, and here we have, you see, if you read the book by Intropera, you will see that in the solution of heat transfer through a fin there are 4 types of boundary conditions. We have considered only one type of boundary condition where the fin temperature is known at the fin base, and the heat transfer rate is considered to be 0 at the fin tip. That is one boundary condition. There are other boundary conditions, like where the temperature is known at the fin base as well as at the fin tip. That is the second type of boundary condition. Third boundary condition is also there, where we consider a very long fin. And there is another boundary condition where the entire heat entering into through the fin base is going to the surrounding fluid by convection from the external surface. So these 4 boundary conditions are there. Out of that, we have considered only 1 boundary condition. So our experiment is based on this 1 boundary condition. So as I was, you were asking, the fin is inserted inside the duct, and it is covered by, fin is covered by moving air. The air is moving perpendicular to the this axis. This is x-axis, you can say. You consider a perpendicular axis. In this perpendicular direction, air is flowing. So we are considering the airflow is perpendicular to the length of the fin. And whatever velocity you have considered, that velocity is in the perpendicular direction. Now, any question?
No, sir.
Now, I'll suggest you, after I send it to you today and tomorrow, I'll send something today, something tomorrow. After I send it, you make your own calculations. In the report, you have to make a sample calculation sheet. You understand? You have to make a here. You have to, these things you have to provide. You have to give these things, but you have to find the fin effectiveness also. Here, effectiveness equation is not given. You have to find effectiveness also, but you have to write one sheet which gives the sample calculation, the entire calculation for a particular run. So as you know, that is to be done, and these pages you download, and because the offline classes are starting, it is good for us. You have to take a print out of it, and you have to submit along with the curves and other things. Not now, but when the time comes, because your classes have just started. We are doing 3 experiments now. Other experiments are still to be done. Let us do all those. And then after that, we'll go for the reports and these things. But there is no hassle like that. Any experiment that we are doing in the online mode, you are free to discuss with me in the offline character also, and make the reports, and then we'll see the viva also. Now, now someone was telling that there are some question the previous days. Hello.
Yes, sir. Yes, sir.
কি প্রশ্ন বলো আমাকে?
Sir, can I show you the screen?
Yeah, show me.
স্যার আপনি একটু আপনার স্ক্রিনটা একটু তাহলে অফ করুন, আমি আমারটা শেয়ার করছি।
আমার আগের দিনের স্ক্রিনটা এখন বার করতে সময় লেগে যাবে।
না স্যার, আমি বলছি আপনি আপনার স্ক্রিনটা একটু মানে অফ করে দিন, স্ক্রিন শেয়ারটা, তাহলে আমি আমারটা শেয়ার
অফ করে দেবো।
হ্যাঁ স্যার।
হ্যাঁ, এবার করো।
ইয়েস স্যার, করছি। স্যার স্ক্রিনটা দেখতে পাচ্ছেন স্যার? হ্যালো স্যার,
দেখো জিনিসটা আসেনি তো এখনো।
মানে স্যার আপনি স্ক্রিনটা দেখতে পাচ্ছেন স্যার আমার?
এক সেকেন্ড।
হ্যালো।
হ্যাঁ, দাঁড়াও।
স্যারের মনে হচ্ছে কিছু একটা প্রবলেম হচ্ছে।
আমরা দেখতে পাচ্ছি তো।
না স্যার তো না দেখলে স্যার
প্রিন্টটা দেখতেই পাচ্ছি না।
না আমিও
স্যার আপনার কি
আমিও দেখতে পাচ্ছি না কিন্তু অরণ্য।
অন্যরা দেখতে পাচ্ছিস?
হ্যাঁ আমি পাচ্ছি দেখতে।
আমি দেখতে পাচ্ছি।
আমিও পাচ্ছি।
এবার দেখ।
আচ্ছা আমি আরেকবার অফ করে
অরণ্য তো অফ করে অন কর।
হ্যাঁ। স্যার এবার আসছে স্যার?
না, আসছে না তো, আসছে না।
অন্যরা
কাজ করো, আমরা এটা লিভ করি, করে আবার আমি ঢুকছি। হ্যাঁ
স্যার, আপনি একবার লিভ করে জয়েন করুন স্যার, এটাই বেটার হবে।
লিভ করে আমি আবার ঢুকে দেখছি, ঠিক আছে?
ওকে স্যার, আপনি আমার লিভ করে জয়েন করছি।
আগে আগে তুমি কি চাইছো? আগের দিনের ওই মানে কি বলে থার্মাল কন্ডাক্টিভিটি অফ ইনসুলেটিং রড, ওইটা তো?
হ্যাঁ স্যার, ওই রিগার্ডিং স্যার কয়েকটা ডাউটস আছে স্যার। মানে আমাদের হয়ে গেছে ল্যাবটা, রিপোর্টটা মানে মোটামুটি তৈরি করা হয়ে গেছে, 90% কাজ কমপ্লিট। জাস্ট হচ্ছে কিছু ডাউটস আছে, যার জন্য আমাকে ওই 10% আর
তুমি
কি।
আমাকে বলো না, মুখেই বলো না,
স্যার
না
বেসিক্যালি,
হয় পরে আবার ওটাকে করবো।
স্যার বেসিক্যালি যে প্রবলেমটা হচ্ছে স্যার, ওখানটায় আপনি যে আমাদেরকে ডেটা ভ্যালুস গুলো দিয়েছেন, সেই ভ্যালু অনুযায়ী স্যার এক্সেলে গ্রাফটা পুট করার পরে একটা পুরো স্ট্রেট লাইন কার্ভ আসছে স্যার, মানে স্ট্রেট লাইন গ্রাফ আসছে স্যার। তো এবার স্যার স্ট্রেট
স্ট্রেট
লাইন,
লাইন গ্রাফ আসছে বিটুইন কে অ্যান্ড টেম্পারেচার, থার্মাল
হ্যাঁ স্যার কে অ্যান্ড, হ্যাঁ স্যার, মানে না স্যার কে অ্যান্ড টেম্পারেচার না, টেম্পারেচার অ্যান্ড হচ্ছে স্যার ওই ডিস্টেন্সটা, মানে এক্স, ওই যে রডটা আছে রডটার অ্যালং ডিস্টেন্সটা স্যার,
আচ্ছা, বেশ
টেম্পারেচার যেমন রড।
বেশ বেশ বেশ।
তো
হ্যাঁ, টি
স্যার এবারে
ভার্সেস
তাহলে,
এক্সটা স্ট্রেট লাইন আসছে, তাহলে তো ভালোই হলো, ডিটিডিএক্স তো তোমার একই হবে।
হ্যাঁ হ্যাঁ স্যার, এবারে ডিটিডিএক্স একই হবে। এবারে এবারে স্যার দ্বিতীয় মানে এখানটা স্যার একটা ডাউট যেটা হচ্ছে, ওই মানে ওখানটায় যে ল্যাব শিটের ওপর লেখা রয়েছে যে মানে গ্রাফ থেকে প্রত্যেকটা জায়গাতে মানে আমাদেরকে ডিটিডিএক্স করতে হবে। এবার স্যার আমি একটা দাদার সাথে কথা বললাম, তো ওই দাদাটা বললো যে দেখ ভাই, আমাদের বেলায় আমরা কি করেছিলাম, ওই যে টেম্পারেচার ডিস্ট্রিবিউশনটাকে ওটা স্যার একটা পলিনোমিয়াল ফাংশন হিসেবে ধরে করে নিয়েছে এবারে। মানে স্যার ওরা ওই ইয়েটাকে,
তোমরা করতে পারো পলিনোমিয়াল ফাংশন হিসেবে ধরতে, অথবা তোমরা একটা কাজ করো, ওটা একদম স্ট্রেট লাইনটা আসার কথা নয়, বুঝলে? যাই হোক, ইন এনি কেস তোমাদের এসেছে, ওটা যদি একটু ভ্যারিয়েশন থাকে তাহলে ওখানে তুমি একটা বেস্ট ফিট কার্ভ ধরে নিতে পারো, টি ভার্সেস এক্স, একটা বেস্ট ফিট কার্ভ করে তারপরে তুমি অ্যাট ডিফারেন্ট ভ্যালুজ অফ এক্স, দ্যাট ইজ অ্যাট সিসি, বিবি অ্যান্ড এ, অ্যাট দি থ্রি সেকশনস, তোমরা
স্যার আমি যখন এক্সেলে যখন স্যার ভ্যালুগুলো পুট করেছি, ডাইরেক্ট স্যার ওটা মানে স্ট্রেট লাইন নিয়েছে স্যার। মানে আমি যে বেস্ট ফিট স্ট্রেট লাইন নিজে থেকে মানে তৈরি করেছি তা নয় স্যার, ডাইরেক্ট স্ট্রেট লাইন নিয়েছে এক্সেলে।
এখন শোনো, ব্যাপারটা হচ্ছে কি, আমরা তো অ্যাকচুয়ালি এই যে রিডিং গুলো না, রিডিং গুলো তো আমি তোমাকে মানে আমি তো একটা এক্সপেরিমেন্ট করে রিডিং গুলো পাইনি, বুঝতে পেরেছো তো? যেহেতু এই এতদিন ধরে ডামাডোল চলছে, আমাকে এই রিডিং গুলো ইউনিভার্সিটি থেকেই ওই ওদের ল্যাব থেকে আমি জোগাড় করেছি। এবার যারা আমাকে রিডিং গুলো দিয়েছে, আমার মনে হয় তাদের কিছু ভুল ভ্রান্তিও থাকতে পারে, হোয়াট এভার ইট মেবি। আমি এখন তো আর সেটা কারেক্ট করতে পারবো না, তোমাদের যাই আসুক তোমরা সেইটা, যদি টিটিডিএক্স, যদি তোমার স্টেট লাইন আসে, তার ডিটিডিএক্স টা সব জায়গায় এক হবে।
হ্যাঁ স্যার, সেমই আসবে তাহলে স্যার, ওইটা নিয়ে করবো।
সেম যদি আসে, তোমার তো কিউটা আলাদা,
হ্যাঁ স্যার,
তাহলে তোমার কেটা তো আলাদাই হবে।
এ ডিফারেন্ট হবে স্যার।
হ্যাঁ,
আর স্যার আরেকটা যেটা কোয়েরি এসেছিল স্যার, কে এর ভ্যালুটা, মানে এই যে এই যে রডটার ক্ষেত্রে যে কে এর ভ্যালুটা, সেটা স্যার অনেক বেশি আসছে। মানে আমার ক্যালকুলেশনে স্যার ভ্যালুটা এসছে 4832.28 স্যার। মানে এবার এত বেশি ভ্যালু, এবার আমি স্যার 2-3 বার ক্যালকুলেশনটা চেক করলাম, দেখলাম যে স্যার ক্যালকুলেশন করে একদম এইটাই আসছে, এবং আমার স্যার অন্য জায়গাতে
মানে ওখানে রডের মেটেরিয়ালের থেকে তুমি বলতে চাইছো ভ্যালু অফ কেটা বেশি আসছে, তাই তো?
মানে স্যার মানে আমি জানি না স্যার রডটা কি মেটেরিয়াল দিয়ে তৈরি, সেটা তো ল্যাব শিটের উপর বলা নেই, কিন্তু যা ক্যালকুলেশন করছি সেটা রডের মানে কে এর ভ্যালু এত
না,
বেশি।
সেটা তুমি আগে দেখো যে তোমার ইউনিটস গুলো বসিয়ে ঠিকঠাক
হ্যাঁ স্যার, ইউনিট স্যার ঠিকঠাক বসিয়েছি স্যার। ইভেন স্যার আমি ওই আগের বছর দাদারা যেটা
একটু
করেছিল,
এসেছিল, একটু সময়ের জন্য এসেছিল, এসে চলে গেল। যে আমি বলছি যে তুমি তুমি একটা ভ্যালু গুলো বসিয়ে দেখো যে ওয়েদার
ইউনিটসে কোনো ভুল নেই স্যার। আমি আগের দিন রাত্রে অনেকবার চেক
অনেক সময়
করেছি।
কি হয়, কে এর যে ভ্যালুটা বসাতে গিয়ে অনেকে মানে একটা ইউনিট আরেকটা ইউনিট মিশিয়ে করে ফেলে, তার গন্ডগোলটা হয়। তো সেটা যদি না হয়ে থাকে তাহলে যা হয়েছে হয়েছে, রেজাল্ট যা এসছে এসছে।
মানে স্যার আমি আমার এই ব্যাপারটা একটু সন্দেহ হয়েছিল বলে আমি ওই দাদাদের ল্যাব শিটের ওপর ওই যে ওরা যে করেছিল আগের বারে, তো ওইটার সাথে একবার মিলিয়ে দেখছিলাম যে ওরা যে কনসিডারেশন গুলো করেছে তার থেকে কি আমার কিছু মানে ডিফারেন্স আছে, জানলে এত বেশি আসবে না। তখন দেখলাম স্যার ওরা যা যা করেছে, মানে শুধু ওদের ভ্যালু গুলো ডিফারেন্ট ছিল, যা যা করেছে ইউনিটস যা যা ছিল সবই স্যার আমার সেম করা, বাট আমার ভ্যালুটা মানে ভ্যালুগুলো এমন ভাবে দেওয়া আছে এই ইয়েতে। তো এই কে এর ভ্যালুটা মানে স্যার মানে অনেকটাই বেশি আসছে, অনেকটা, মানে 4800।
ঠিক আছে, যা এসছে এখন কিছু করার নেই, যা এসছে এখন তো আর মানে আমরা এরকম ঝুলন্ত অবস্থায় আর তো বিশেষ কিছু করতেও পারবো না। মানে about the readings, only thing is that if the offline classes start, then I can do the experiment in actual thing. Though I have
আর একটা
experienced
যেটা
reading part, we can take once again the reading.
ওকে স্যার, মানে স্যার
সিচুয়েশন।
ওখানটা আমি একটা জিনিস নোটিস করলাম যে মানে দাদাদের ওই ল্যাব রিপোর্টের সাথে আমাদের যে ডিফারেন্সটা, ওই যে স্যার মানে কুলিং এন্ড আর যেখান থেকে স্যার ওয়াটারটা মানে হিট হওয়ার পর যেখান থেকে ওয়াটারটা বেরোচ্ছে, এই দুটো টেম্পারেচারের ডিফারেন্স আমাদের ক্যালকুলেশন অনুযায়ী, মানে আপনি আমাদেরকে যে ডেটাটা মানে দিয়েছেন সেইটা অনুযায়ী 13 ডিগ্রি ডিফারেন্স আছে। আর দাদারা যেটা করেছিল ওখানটায় স্যার 3 ডিগ্রি ডিফারেন্স ছিল,
কত?
যার জন্য স্যার 3 ডিগ্রি স্যার, 3 ডিগ্রি, 3 ডিগ্রি
না না,
ডিফারেন্স।
তুমি তুমি আমাকে বলতো, আমি পড়ানোর সময় বলেছিলাম ওখানে রিডিং গুলো যেভাবে লেখা আছে একটা জায়গায় রিডিংটা ভুল ছিল।
স্যার একটা জায়গায় বলতে আপনি বলেছিলেন যে একটা 87, ওটা 89 এরকম একটা বলেছিলেন, আমার মনে আছে
না
স্যার।
না, একটা জায়গায় মানে মানে ড্রপ ওই টেম্পারেচারটা, ধরো তোমার ওই আমি বলছি তোমাকে T10, 11, 12, 13, ঠিক
হ্যাঁ
আছে?
স্যার।
আর 10 থেকে 11টা কম হবে, 12 থেকে 13টা কম হবে। তো সেখানে ওটা উল্টো ছিল আর কি।
স্যার মানে
ওইটা
ওখান
ওইটাকে দেখো আর কি, ওইটা দেখো, আমার মনে হয় ওইটা মানে রিডিংটা ঠিক আছে কিন্তু উল্টো লেখা আছে।
উল্টো লেখা
আচ্ছা,
আছে।
আমি একটা কাজ করি, আমি ওই শিটটাকে মানে বার করে তোমাদেরকে আমি শিগগিরই আরেকটা ক্লাস নেব, তখন আমি ওটাকে দেখিয়ে আবার তোমাদের বলে দেবো, ঠিক আছে?
ওকে স্যার, আপনি একবার একটু কে এর ভ্যালুটা একটু দেখুন, দেখবেন স্যার কিরকম
আচ্ছা
মানে
ঠিক
আসছে
আছে,
অর্ডারটা।
ঠিক আছে, ঠিক আছে।
ওকে স্যার।
ওকে।
ওকে স্যার, থ্যাংক ইউ স্যার।
আচ্ছা, এইটাকে আমি আজকে কিছুটা পাঠাচ্ছি, কালকে আমি ওই ফ্রন্ট পেজে যে ডেটাগুলো আছে, ফ্রন্ট পেজে ওই ইনস্ট্রাকশন শিটের ওইগুলোকে আমি কালকে পাঠাবো, ঠিক আছে? আর তোমরা যদি কালকে যাও, তোমরা আমাকে একটু জানিও যে তোমাদের কি হলো আর কি, মানে
স্যার আমরা মানে বেশ কিছুজন কালকে ইউনিভার্সিটি যাচ্ছি, বিকজ আমাদের স্যার একটা ক্লাস অফলাইনে হবে বলা হয়েছে, মানে ওই মেশিন ডিজাইনের ক্লাসটা। তো আমরা যাচ্ছি স্যার কিছুজন ইউনিভার্সিটিতে, মানে আমাদের A1 সেকশন থেকে, আর অন্য সাবসেকশন তো ওদের যাচ্ছে, ওদের সেশনাল আছে, ওদের যেতেই হবে। তো
বেশ,
স্যার।
ঠিক আছে।
ওকে স্যার। স্যার
হ্যাঁ হ্যাঁ
হ্যাঁ স্যার, এটাও একটা স্যার রিকোয়েস্ট, মানে আমাদের যে ল্যাবগুলো ধরুন 3টে ল্যাব আজকে নিয়ে 3টে ল্যাব আমাদের হয়ে গেল, তো অফলাইন ক্লাস ক্লাস তো স্টার্ট হচ্ছে যখন, মানে এগুলোকে একবার দেখিয়ে দেবেন, মানে এই যে
হ্যাঁ হ্যাঁ, দেবো, ওইগুলো
ওকে
নিয়ে
স্যার।
চিন্তা নেই। আমরা দেখো, আমরা তো আর মানে ক্লাসটা না করে তো থাকতে পারবো না, ক্লাসটা করলাম, আমি আমার মানে যতটা সম্ভব আমি বোঝালাম তোমাদের। এবার তার মানে এই নয় যে এটা এখানে শেষ হয়ে গেল, আমি আবার একটু অফলাইন খুললেই আমি আবার তোমাদেরকে রিডিং ফিডিং নিয়ে দেখিয়ে দেবো,
ওকে স্যার।
যে মানে as regards the classes are concerned, আমি always there with you, কাজেই কোনো অসুবিধা হবে না। তোমরা যদি রাজি থাকো, I will continue doing classes and I'll take the readings to whatever times। তুমি যদি মনে করো 2 বার 3 বার নিতে হবে, আমি সেটাও নেব, there is nothing wrong about it, ঠিক আছে?
থ্যাংক ইউ স্যার।
Thank you. Okay then.
এ তোরা লিভ করবি না, একটু দাঁড়া।
আরে মিটিংটার হোস্ট কে ছিল? স্যার লিভ করলো,
সোহেল ছিল, সোহেল।
আচ্ছা, আমার কথা কি শোনা যাচ্ছে?
হ্যাঁ শোনা যাচ্ছে।
হ্যাঁ শোনা যাচ্ছে, খুব সুন্দর আওয়াজ।
আচ্ছা এবার দাঁড়া, আমি স্ক্রিনটা প্রেজেন্ট করছি, তো এই আমাকে সোহেল বলতো আগের দিন স্যার এরকম কিছু বলেছিল, কারণ আমার তো মনে নেই, আমার শুধুমাত্র একটা জিনিস মনে আছে, বলেছিল যে 87 না ওটা 89 লেখা হবে, মানে 89 হবে ওই যে অবজারভেশন টেবিলটা।